All right, we are now recording in Chapter 12. I have a feeling there's nothing in Chapter 12 left to show because I think that was the last slide they had up there, so nothing else is in there. We'll see, but we'll go on to the next chapter. Well, let me say this. There's two kind of important pieces of information. Most of you have been here for at least the last couple of weeks, okay? If you have, or if you've been listening, hopefully you heard this. We are not meeting in here on Thursday, okay? Last week, both days last week and tonight, we're doing an extra 30 minutes. We're going from 4 to 6, basically, rather than 4 to 5:30, okay? So we've made up the class. After tonight, we'll have made it up. The hour-and-a-half class. So I've got to leave town, and it was just going to be so late getting over to Georgia. My wife didn't want to drive that late, and I knew I shouldn't be driving that late. So we're going to leave a little bit early. I cleared it with my boss. Everything's been cleared. So we will not meet at all here on Thursday. We will go an extra half hour tonight. If you missed any of the earlier ones or had to leave early, everything's recorded. It's out there on YouTube, so you'll be able to pick up anything you may have missed. That's one reason we're a little ahead of where perhaps we should be, but that's because we're going to miss class on Thursday. But we're moving along okay, I think, for covering the material in the course. All right, any questions on anything that we've covered so far? All right, as I said, we were on Chapter 12. And Chapter 12 is the chapter on matter. And in your course description, this was, I can't remember how it was phrased, but it was something like something about matter. So that's why I chose this chapter. Phases of matter, states of matter, interactions of matter, something like that. So in Chapter 12, we're on example 5 on page 332. So if there's no questions, we will continue. Now, example 5 says, a quantity of gasoline weighs 5.50 pounds. Okay, what is that a measure of? 5.50 pounds. Almost gave it away in the sentence. What was it? Quantity of gasoline weighs. So this is what would be the noun form for weighs? What is way too many pounds? Earth to class, come in please, okay? Weight. And what's the symbol for weight? This book uses one that's a little different from most. F sub W, is that what you said? Yeah, okay, F sub W, that's the weight. With a weight density, gasoline has a weight density, and what symbol do we use for that? Huh? Yeah. Okay. Is it capital D? Yeah, that's right. So, and this is I said D sub W and wrote W, okay? I can't get my eraser to come up. There it is. Okay. All right, so D sub W is, and this is for gasoline, 42 pounds per cubic feet. I can't write. That's pounds per cubic feet. Let me see if I can make that look a little bit better. Okay. Close. Okay, pounds per cubic feet. Find the volume. So we're looking for volume. How will we do that? Folks, units are your friends. And you might even want to use one of those little triangles or circles if you find them helpful.
Would it be the L sub W
That's it exactly. So now here's how I do it, because I'm just sort of really simple-minded. I'll look at D sub W, and that is 42.0 pounds per cubic foot, okay? And I'll look at that and say, well, pounds must be in the numerator because that's where it is there. So that's going to be my 5.50 pounds, and my denominator is going to be cubic feet, so that must be the volume in cubic feet. And sure enough, that is. And if you sort of switch the places between the V and the 42, in other words, multiply both sides by V and divide by 42, you get V is equal to 5.50 pounds divided by 42 point, I can't write. Okay. 42.0 pounds per cubic foot. There again, I can't write cubic feet. Okay. Now, notice here the pounds will cancel out. Okay. Leaving us as a unit 1 over cubic feet, which you can take that denominator and flip it, and that'll be cubic feet. So this is going to be an answer in cubic feet. So if anyone has a calculator and want to punch that in, see how violent we are in the South. We punch in our numbers, not press them. Okay, 5.50 divided by 42. Anybody? I don't have a calculator on me. Second? 0.1309. And that would be in cubic feet. Now that's a pretty small number, okay? Oh, and that's how they leave it though, okay? I was thinking they probably wanted that in cubic inches, and we were going to do a conversion, but they left it. But notice what they did. We only have 3 digits here, 3 digits here, so we only use 3. Count off. 1, 2, 3. Look to the right. That's more than 5, so make that a 1. 0.131 cubic feet. Okay, that's why they did that. Hang on to the digits until you get to your final answer, then round it to whatever you need to. Okay? Any questions? Pretty straightforward problem there. Your circle or triangle might work very nicely in a problem like that. All right. Now this is not an example, but it's leading up to one. Before this, either they've given us the dimensions of a rectangular solid and you calculate the volume, or like in this problem, that's what you're looking for. So based on density and weight, you could determine the volume. But sometimes what you have, in fact, the lab I'm going to do Thursday with my physical science class, we're going to be calculating the density of 2 types of igneous rock, one granite and one basalt. Okay? And a piece of rock is not something you can measure the dimensions on very easily because it's irregularly shaped. So this is giving you a procedure whereby you can do this. Okay? The density of an irregular solid rock cannot be found directly because of the difficulty in finding the volume. However, we could find the amount of water the solid rock displaces, which is the same as the volume of the rock. And that's exactly what we're going to do in the lab on Thursday in my other class. I'm going to have this container up on a ring stand as full of water as I can get it. I mean, to the point it's hanging over the edges but not spilling. Okay, full as I can get it, and we're going to put under it a larger container that's going to catch the water. We're going to very slowly lower the rock into the water. Water is going to spill out the container, caught in the one below, and then finally let go right before your fingers reach the surface. And the amount of water we're going to get, we're going to measure its volume. That's the volume of the rock. So that's exactly what they're talking about here. I wish there was a picture of it, but I'm pretty sure there's not. Let me just see. It's going to be a pain in the neck if it's not. Okay. Nope. That was the density table, and that's the last slide. So we don't have any more slides there, so I'm going to go on and close that out. So let's go back to current slide. All right, but you see the pictures in your book. Anyone still doesn't have a book or access to one? This won't be as good as looking at it, but please. See, there's a container with water in it. Now, the key here is to have water right up to the level that another drop, in fact, what I do is add water until it runs out of the container, get it to right at the point where it's right before it runs out, empty that, okay, put it back, then lower the rock in, and then collect the water in the container. Measure the volume of water there, that's the volume of water in the rock. Now that wouldn't work if the rock floated, but most rocks don't float, so no problem there. Okay, so that leads to example 6. A rock of mass 10.8 kilograms. Okay, let me get my pen back. All right, they told us the mass is 10.8 kilograms. Not a tiny rock, okay? That's pretty hefty little old rock, okay? That would be 25 pounds or so. That's kilograms. 10 point, where is it? I lost it. There it is. 10.8. Where did I get? Oh, I know that. That was not a 1 there. That was part of my K. I didn't get to write the rest of it because my pen messed up. Okay. 10.8 kilograms, that's the mass. Displaces 3200, with the first 0 being significant, cubic centimeters of water. Okay? What's that? What's that a measure of? 3,200 cubic centimeters. Volume, that's your volume of the water. Whoa, I can't write a V either. Try that one more time. Volume of the water, okay? What is the mass density of the rock? So what are we looking for? Which symbol is? D sub M, mass density. And how do we measure mass density? Okay, it's mass divided by volume, mass density right there. And we have the 2 units we need, or 2 numbers we need. We have 10.8 kilograms divided by 3,200 cubic centimeters of water. Now, there's a little something off here. And what is it? What's that? Yes. Most of the time, if we're using kilograms as our mass unit, what do we use for our volume unit? Meter, okay. So before we do that, let's take this out of there for now and fiddle with our units. We like fiddling, don't we? Took it in music appreciation, right? All right, 3,200 cubic centimeters. Okay, and we're trying to change that, so we do a conversion to cubic. Say cubic. Get out of here. Okay. Eraser was what I was looking for. Okay. We're trying to get to cubic meters. If I can ever get my hands and fingers and pen to work in conjunction. Okay, so what are we going to have to do? What do we do first? Fiddle with numbers or fiddle with units? Second? Units always. That's the second line. What unit goes where? Something goes on top of the line, something goes on bottom of the line. What goes where? 1 meter. Excuse me? Okay, sorry. Where do the units go? Above or below? What did you say?
Above 1 meter.
Okay, cubic. Okay, a meter goes above the line. That puts centimeters below the line. And what you say, 1 meter is how many centimeters? 100 centimeters. But we don't have meters and centimeters. We have cubic meters and cubic centimeters. So we're going to have to cube the units and cube the numbers. Now, 1 cubed I can do. That's 1. 1 times 1 times 1. Okay. 100 cubed, however, is what? Actually, yes, you triple the number of zeros. You have 2 zeros there. That's 1, 2, 1, 2, 1, 2, because you're cubing it. Okay? So that's 1 million cubic centimeters makes 1 cubic meter. Okay? Now, if you find that hard to believe, go back and picture what your cubic centimeter is. Cubic centimeter is about like the area of your 2 fingernails, little fingernails there. That's a, okay, I mean it's a volume. It's the length times width times height, okay? So it's that little bitty sugar cube, okay? Your cubic meter, on the other hand, picture your doorknob, okay? That's about a meter off the floor. And that door is about a meter wide. And 1, 2, 3 tile out here, something about here, would be about 1 meter from the door. Okay? So, picture you had a box, this wide, this long, that wide, and that high, and you put those little bitty sugar cubes in. It would take $1 million to fill that huge box there. Okay? So sure enough, that's not an unreasonable number. Okay? So, what we've got here is our cubic centimeters cancel out. We're through with those. And here's our cubic meter. Well, we need to move a decimal. This decimal has to move 6 places to make a 1 there. So let's move 3 places, and we're going to put 2 more zeros in front, and that will be 6 there. So this will actually be 0. I like to put a 0 in front too. 0, 0, 3, 2, 0. Now that last 0 is significant. I don't have to put a 0 there for the one who's not. Okay? So that's my volume in cubic meters. So that's what I'll put in the denominator here. 0.00320 cubic meters. Okay? Now, you do the math. You got the calculator? Do it. Sorry, my nose is running. It's going to be a pretty big number, folks. That rock is fairly dense, and this is not the units to use for density. Kilograms per cubic meter. That's enormous. Like I said, picture a rock that's as big as I just said. That's going to weigh more than a ton. See what you get. Anyone? 10.8 divided by 0.0032. You don't have to put the third 0 in your calculator. It doesn't care. 3,375 kilograms per cubic meter. That sounds reasonable because that would be equivalent to 3.38 grams per cubic centimeter. Okay? And that's a reasonable density. Now, I know the book probably doesn't use that unit. They round, again, 3 digits. Yeah, 3 digits here, 3 digits there. Round to 3. 1, 2, 3, count off 3 digits. That's 7, look to the right. 5, that will bump it up 1. 3,380 kilogram per cubic meter. That's a lot. 3,000 kilograms is equivalent to more than 3 tons. So that rock, that would be that block I put there, if you had a rock that big, be about 3 1/3 tons. I don't want to mess with numbers that big, okay? Everybody see how that works? Any questions? Okay. All right. Let's move on to example 7. This is fairly similar, only, I'm sorry. Let's start with clean sheet here because I don't want to be running out of room. A rock displaces 3.00 gallons of water. What a unusual rock to be exactly 3.00 gallons water. That's what it displaces. Has a weight density, we know this up front, so D sub W for the rock is 156 pounds per cubic foot. There, I did it again. Okay, I can't write cubic feet. Okay, sorry. Why? I've got the sneezes and nose running, and I don't know what's going on. Okay. What is its weight? That's the question. And you told me before this is F sub W. This is the unknown here. Okay. Now, already something looks a little suspicious in the problem. What's that? Units. Yeah, that's usually the things that look suspicious. What were we given and what kind are we looking, well, not looking for, we're looking for weight, but what's the discrepancy here? Gallons, and we need it in cubic feet. Okay? Now, I'm trying to remember, I don't recall finding in this book a table that does conversions like that. Most physics books I've ever dealt with and taught from will have such a table. This one does not, that I can find. If anyone's found it, let me know. But I know in an earlier problem, and probably from earlier chapters, ones that we didn't do, okay, what's that? Okay, what is that? 0.124 is what? 134. And what is that? Cubic feet per gallon? That sounds reasonable. Okay? Picture a gallon jar of pickles or something like that. And a cubic foot is 1 foot by 1 foot by 1 foot, so that's a little bit bigger, so there'd be a smaller portion of that would be, okay. So that sounds reasonable. Let's go with it. So first thing we're going to do is multiply this by a blank blank in order to get a blank cubic feet, right? That's what we're looking for. Okay? So what do we deal with first? Numbers or units? Units. What unit goes where? Gallon goes on the bottom. Perfect. And cubic feet on top. And that's our conversion right there. 0.134 cubic feet in 1 gallon. You got it. So now we just multiply. And I think I can even multiply that. That would be a 2 there. That would be a 0 there, and that would be a 4. Yeah, 4 there, 0.402 cubic feet. Okay, so now that we know this is our volume, we know our density, and again, you can remember formulas, you can do the circles or triangles if you want to, but frankly I use units, and I see that 156 pounds per cubic foot is equal to so many pounds. We don't know, that's what we're looking for, so that's our F sub W, over so many cubic feet, 0.403. Well, if we're looking for this, what we do, and this is cubic feet now, is multiply both sides of this by 0.403 cubic feet, and multiply this by 0.403 cubic feet. Okay, so these, you lose them on this side and you wind up with F sub W. I'm going to switch sides now. Okay, see, the units are helpful. These cubic feet cancel out those cubic feet, and you're left with just the numbers. 0.403 multiplied by 156, and what do you get? 0.403 times 156. $62 point what? 868, and the units will be pounds. Okay? Now, I'll look up here, 3 significant digits there, 3 significant digits there. You gave me 3 significant digits, so I'm going to count off 3 digits. 1, 2, 3. Look to the right. It's a 6, which is greater than 5. That'll raise that to a 9. So it'll be 62.9 pounds. Okay, they probably rounded more poorly than we did. Okay, let's see how they did it. 62.6. Okay, well, let's see what they did. They said, look at how they did it. They did 231 cubic inches in a gallon, and then they did 12 inches in a foot and cubed both, and they went through all sorts of things. Where did you get your number? Something you had looked up before, or did you find it in the book? No, I mean the 0.134 that we used. We Googled that last week. Oh, we did? Okay, okay. Well, Google may have rounded to, I don't know, but that's close enough. They did 2 or 3 steps where we did 1 using Google. So, right. And I don't know how many digits that was correct to, if it was 3 or if it needed to be rounded or something. But it's close enough. That's close enough. Okay. Now, if you'll notice, I don't guess I've given any tests back because there's still some people who haven't turned in the first test. So I need those in before I can return any test to you. So if, word to the wise, please, if you haven't turned it in, get those in as soon as you can. All right. Now, sometimes we don't like to use density because density always carries with it some units, like pounds per cubic feet, kilograms per cubic meter. You know, big, bulky units. Sometimes we prefer just to talk about relative size or densities. And to compare densities of 2 materials, we compare each with the density of water. Okay? Now, the specific gravity of any number, so let me write this down. I think I'll go to a clean page here so it'll be a little bit better. Because, is there still anyone without a book? Does everybody have a book? I see. Do you have one? Yeah. Oh, you do. You got one, T? Yeah. Oh, okay. So I don't have to write this down. I don't know if any people listening at home, but if not, if so, jot it down quickly. To compare the densities of 2 materials compared to the density of water, the specific gravity, the book uses SPGR, specific gravity of any material is the ratio of the density of that material to the density of water. Okay? So the density of the material to the density of water. Now, what does that do for you? Okay? So specific gravity is equal to the density of the material to the density of water. Now, a couple things to note here. They don't say which density. They don't say which units. They're just saying specific gravity. Okay? So, if by chance that is a mass density of the material, then use the mass density of water. If it's the weight density of the material, use the weight density of water. If it's in pounds per cubic foot, use it for both of them. If it's for grams per cubic centimeter, use it for both of them. If it's kilograms per cubic meter, use both of them. But specific gravity, basically your units cancel out. And here's the good news, folks. The specific gravity of any material, it'll never change. No matter what unit you're in, no matter anything else, it's a ratio. Dimensionless. It's just the ratio of that density to that of water. Whatever units you're using. Okay? So, the density of iron, this is example 8. So the density of iron, I'm going to call it Fe, is 7830, and that is kilograms per meter cubed. Okay? Find its specific gravity. Uh-oh. How do we do that? What else would we need? The density of water. And does anyone happen to know what that is? Now, I'm awfully sorry that I took off my last thing, but it's in, yeah, what is it? 1,000 what? Kilograms per cubic meter. I say that because you need to make sure you've got the same units. So what's specific gravity for iron then? Second? 7.83. You can do that division in your head. No units. 7.83. If we're measuring the density of iron using grams per cubic centimeter, that's exactly what it would come out to be. 7.83 grams per cubic centimeter. If we're measuring it using pounds per cubic foot, once you divide by the density of water in pounds per cubic feet, you get this exact same number. This is the specific gravity of iron no matter what unit you use to measure your density. That's the beauty of specific gravity. It's fixed forever for any given material. Okay? No matter how many tons you have or how many ounces you have or how many milligrams you have or how many kilograms you have. It's the specific gravity is that. They got 7.83 also, good for them. Ready for example 9? Can I erase? The density of oil is 54.2 pounds per cubic feet. 52.4 pounds per cubic feet. Find its specific gravity. What would that be? Anybody? What's that? It's going to be a division. You got that right. What will we be dividing into and by? Okay. Density of oil divided by the density of water. Just make sure you use the same units. Okay? And this was... Say again? You're right. I can't read or write or something. Okay. Let's try that again. 54.2? Okay. 54.2 pounds per cubic feet. So 54.2 62 pounds per cubic feet. So what had I better list my density of water in? Pounds per cubic foot. Okay, does anyone know that number? 62.4 pounds per cubic feet. So, pull out your handy dandy calculators, see what you get. Wait one second. 0.8685. Is that what you said? Okay. These both have 3 digits. So count off 3 digits, significant digits. 1, 2, 3. Look to the right. There's a 5. That means bump that up to a 9. So 0.869 is specific gravity of oil. Okay? That's it. No units. Okay? How'd the book do? Yes, they got it too. Good for them. Okay. What's that? Yeah. Now I'm wishing I hadn't deleted the table that was on the very beginning, because that table had all these densities in them. So I could have used it, but I did delete it when I saw I wasn't going to use it. Well, that we were already past it. Okay. Now, here's a little deal here. In general, the specific gravity of water is, then what would it be? Specific gravity of water. It's the density of water divided by what?
The material.
No. Water is the material. So it's density of water divided by the density of water, which makes that 1. When you divide any number by itself, it becomes a 1. Okay? So, if a material is denser than water, it'll have a specific gravity greater than 1. If it's a material less dense than water, like oil, it'll have a specific gravity less than 1. And that's what we're dealing with. So a material with a specific gravity less than 1 is generally going to float on water, and a material having a specific gravity greater than 1 is going to sink in water. Now, a hydrometer is a sealed glass tube weighted on one end. And let's see, y'all probably aren't going to use any hydrometers in sonography, are you? Do you use it anywhere now? Do you determine the density of blood? So I'll let you read or look at or deal with that. I really then don't see there's no more problems, so let's move on. But where you do see that sometime, you ever going to have your radiator checked? And they get this little device and put it in your radiator to see what your specific gravity of your water in that is. That's a hydrometer. They're sometimes called hygrometers too. I don't know why, but they are. But anyway, it lists several things. A new battery, its specific gravity of the liquid in there would be about 1.3. If it's old battery, you'll find it's dropped to 1.15 or somewhere in that time number range. They also give the temperatures, different temperatures, how they affect. A warmer temperature is probably going to lower the specific gravity because the molecule is moving faster and farther apart, whereas a colder temperature is going to increase the specific gravity because now the molecules shrink. They get a little closer. Okay. And this is antifreeze in water solution, so you don't quite have the same specific gravity anyway. Okay? And then just a specific gravity of some common liquids at room temperature. Benzene is 0.9, ethyl alcohol 0.79, gasoline 0.68, kerosene 0.82, mercury, way out to lunch here, 13.6, seawater 1.25, sulfuric acid 1.84, and it goes on. Okay. If you need some more problems, oh well, for 12.5, any of the odd number problems 1 through 37 would probably be good. You could do some in each group. There's no reason to do them all. If you want some more things to practice on, the review problems on page 340, the odd numbers for those, I think, are also in the back of the book. Now, it seems like I looked before. Is it only odds? I think they are. I don't believe they put, even for review questions, they put the evens, do they? Let me see. Review problems. No! Looks like review problems, they do put them off. Okay, let me just check out chapter 12 and make sure I'm telling you right. Okay. Chapter 12. Okay. The problems are odds. If you are interested in looking at the review questions, that's on page 339 and maybe on to 340. Yeah. All of those, even and odds, are given. Okay? For review problems that I was just looking at, all of them are given, even and odds. And the review applied concepts, they have 5 questions there, and all 5 of those are given in fair detail. So the review questions, all of those are back there. Okay. So that finished chapter 12. To where do we turn next? Let me get out of here and go to here. Yeah, okay, here we go. Okay, we did chapter 5, we did chapter 8, did chapter 12. It looks like the next one is 16. Make sure that's correct. I'm pretty sure it is. 5, 8, 12, 16. Wave, motion, and sound. Hey, that sounds pretty important for sonography, doesn't it? I think I just lost my place. Okay. So if you haven't found it yet, it's on page 425 is where it begins. So let's start with 16 here. All right. Okay. We're going to start on current slide. Okay. Okay, chapter 16 deals with wave, motion, and sound. And the first thing we're going to talk about are characteristics of waves. Okay? Now, what does a wave do anyway? You may not have thought about it in these terms, but it transfers energy. Okay? What does a tidal wave do? You have an earthquake somewhere, and there's a lot of energy given off, and the tidal wave carries that energy for a long, long way. There was a tidal wave that happened from an earthquake in Alaska, one of the strongest ever recorded, and it was near the coast and created a tidal wave that made it all the way to Hawaii and did extensive damage there. It's hauling energy. That's basically what a wave does. Are there any waves in this room right now? Yeah, if you're hearing me, you're hearing sound waves, yeah. Or somebody else talking. That's sound waves. And that's carrying energy because I'm producing the sound by forcing air through my larynx and making the vibrations. If you hold your hand in front of your mouth when you're speaking, you'll feel the little pulses of air. That's the wave, and it makes it to your ear responds to it, and through the electrical system, an incredible electrical system your body is, it translates those vibrations into sound, okay, that you can understand. Pretty remarkable, okay? A wave transfers energy, okay? So energy may be transferred by the motion of particles. It may be transferred, and this is something else I was getting at. What are you doing with your phone right there, or your computer? How are you able, do you see anything with either one of them? Yeah, how are you doing that? Second? Okay. You are picking up a signal somewhere, and that's translating to that. Yeah, there are tons of waves in this room. If I had a radio in here, I could turn it on, and I could probably pick up 40 stations right here. All those waves are all over in the room. Those are electromagnetic waves. There's no particles being moved in that, but they're still transmitting energy. Because that tower, wherever it is that radio is being transmitted from, they're providing a lot of energy, a lot of power to that tower, and that's being dissipated all over the area. Okay? Whatever you're looking at there, it's your cell phone is picking up electromagnetic waves too. So all this is energy transferred either by the motion of particles, but also by wave motion. The sun's energy gets to Earth. There's no particles out there to speak of in space, so it can't be traveling by particles, traveling by electromagnetic radiation. Okay? So all these are transfer of energy for communications or whatever. Sometimes it's light waves, sometimes it's sound waves, sometimes, it could be just about anything. So what is a wave? A wave is a disturbance that moves through a medium or through space. A disturbance that moves through a medium or through space. Moving through a medium, it's usually moving particles. Moving through space is moving through an electromagnetic field. Okay? Now, Figure 16.1 in the book shows a series of probably pretty massive balls in between springs. Okay? And you can imagine if you were to perturb, like hit on a ball, bounce it one way or another, it's going to get all of them moving. Okay? Because of the change in the elastic medium, the springs. Okay? Now, another term, a pulse, is a non-repeated disturbance that carries energy through a medium or through space. Okay? That was a disturbance. Made my voice do that, and it carried the energy to your ears. You probably didn't want it to get to, but it did anyway. Okay? Non-repeated disturbance that carries energy through a medium or through space. Now that was a medium. Air. Air molecules were forced closer together, further apart. That's what carried the sound. Okay. If the pulse is repeated periodically, then a series of crests and troughs will travel through that medium. Okay? And that is what we call a traveling wave. Okay. Now I use this example in my class earlier today. I was a weird kid, I'll admit that out front. But when we used to be out in the yard and we had the hose, water hose, stretched around the yard, I just loved to pick up that hose and go like this. And what happened then? Have y'all ever done it? What happened? Yeah, it does waves down. It runs out after a while, but you make a wave, a disturbance, okay? And that disturbance is transmitted down the hose. Now, it doesn't take long till it wears out because the hose is heavy and it has a lot of friction in it that resists the motion. But you can do it. And watch it do it. Try to make it go faster and harder and higher, you know, and watch the different things. Okay? Now, what kind of wave is that? That's called the transverse wave. Because my motion is like this, up and down, but the wave travels that way, perpendicular to the wave motion. That's a transverse wave. My speaking right now, the compressions and rarefactions in the air, forced by my larynx and stuff, that goes back and forth this way. And that spring that they showed earlier, if you make your disturbance like this, if you're holding the ball at the end of that spring that's in your book, and you do like that, then you'll see that wave go down the springs toward the end where it's fixed. Okay? That is called a longitudinal wave. That's the motion is in the same direction as the propagation. A transverse wave, the disturbance is perpendicular to the transmission of the wave. Okay? Now, for a transverse wave, disturbance in the medium in which the motion of particles is perpendicular to the direction of the wave motion. Water waves are sort of like that. Okay? And this sort of is what you can think of as a water wave looking like. Let's talk about a few of the characteristics of this wave then. Okay, and again, the motion of the particle is up and down. The direction of the wave is this way. Okay? Now, what we call the amplitude of the wave is the maximum displacement from the equilibrium position. Okay? The equilibrium position is the middle position. That's where things started with before it went up and down. So that would be equilibrium. The maximum displacement from that is what we call the amplitude, whichever way you're going at it. Okay? Up here or down there. Maximum displacement is called the amplitude. Okay? Any part of a wave from the equilibrium or rest position. Okay? Now the longitudinal wave, it's a little harder to measure the amplitude of that. Okay? Because you don't have a screen like this to show. But it can be measured by, you know, the amount of compression, you know, or rarefaction, that type of thing. All right, let's talk about another term. Now, they don't illustrate it here, but I'll mention it. From this point to the next equal point, that one, this is called the wavelength, because that's a displacement here. The wave is moving that way, so from here to here is one wavelength. Now you could measure it from here to here. That would be fine. You could measure it from here, but where would you have to go to? Here? No, the next one. Not only must it be the same position, that's the same position, but it must be going in the same direction. So from here to here would be one. From here to here would be one. From here to there would be one. Not there, because that's going in a different direction. Here. Same position, same direction. Okay, does that make sense? That's one wavelength. Measured in length. Centimeters, meters, feet, yards, furlongs, whatever it happens to be. The symbol for a wavelength, let me make sure this isn't on a different slide. Okay, let's talk about this. Here is your longitudinal wave. This is a spring type action. Now what you're doing here, just so you don't get the wrong impression, here's a spring in equilibrium. Nothing's happening. Okay? What you do, I wish they'd show this, you do that and then pull it back. This is the compression, that's the pullback, that's called the rarefaction. Compression, rarefaction. Look at what happened here. Right after you did it, the compression has moved from here to here. You don't see the rarefaction yet. Down here, the compressions move from here to here. The rarefactions move from here to here. Now, they don't draw the rarefaction too well. Okay, sorry about that. They just show the compression, but they got to pull back, or you'd think they would be pulled back. Okay, so you see, again, your here to here would be perhaps a wavelength. It's harder to illustrate that in a longitudinal wave unless you have a series of them. Then it's a little bit easier to see. So let's go one more. Here we go. This shows the wavelength. Just like I was describing before, there could be peak to peak, valley to valley, or equilibrium to equilibrium as long as they're going in the same direction. Can't be this equilibrium to that because they're going in different directions. Okay? Or it could be anywhere here to anywhere there as long as it's same position, same direction of motion. Usually we go peak to peak or valley to valley. Those are easier to pick out and to do. Okay? So there's wavelength. The symbol for that, have y'all seen that one before? Looks like a little teepee or something, doesn't it? What that is a lowercase lambda. Greek alphabet, whereas here we'd say, how would you represent length? L? Well, in representing wavelength, you go to the Greek alphabet and use their L, which is they call a lambda. So that's what their L looks like. It's called a lambda. Lowercase, by the way. All right. Now there's another thing that we use to characterize a wave, and that is its period. Okay? Now, the wavelength is the distance from here to here. Now, imagine this is a traveling wave. We just happen to take a snapshot of it here, but the wave is doing like this. It is moving down this way. By the time this peak gets to the same position down here, one wavelength away, the time it took to get there is the period. The period is the time between equal positions on a wave. Okay? Whereas the length, wavelength, is the distance between those positions. The period is the time. Time required for a single wave to pass a given point. Okay? Now that we have those two things, let me just make sure this is on another slide. No, I don't think so. Okay? Here's another one. And I'm going to write it in here. Get my pen back to black. Frequency. Now I use F. Let me see what they use. They don't seem to use, okay? Let's call it L for now. Frequency is how many cycles happen in a given time, like cycles per second. Now, cycles isn't a unit. It's cycles per second. Now, let's go back to the period, and usually that's capital T, but for right now I'm going to call it P for period. That's the time length for it to travel one cycle. So that would be time per cycle. So guess what? Frequency and period are reciprocals of each other. Look at the units. This would be cycles per second. This is seconds per cycle. So they're exactly reciprocals of each other. If you know the period, hit the 1 over key, the x to the minus 1 key, invert it, divide it, whatever you want to call it, and you've got the, let's see, what did I say? The period, you got the frequency. If you know the frequency, invert that, you got the period. Okay? The frequency is the number of complete waves passing through a given point per unit time. The common unit for frequency is this is frequency now, is the hertz. That's the SI unit for frequency. And if you're writing it in fundamental units, this is a per second. Okay? Second to the minus 1, because look at this. Cycle is not a unit, that is just a per second. That's what a hertz is, a per second. Now, why HZ? And why do you capitalize the H? Named after somebody. Heinrich Hertz. Good Irish name, no, German name, okay? Where 1 oscillation per second is 1 hertz, or 1 per second. The way they write it here is a 1 over second. 1 per second, okay? That's what a hertz is. Now, in most of the stuff y'all will probably be measuring, you aren't going to measure in hertz. You're going to measure in bunches of hertz, okay? Lots of hertz. No. If there's 1,000 of them, we'll call them kilohertz. 1,000,000 we call a megahertz. Will you go any higher than that? You will? Okay. What's the next one? Gigahertz. Okay. You could go as high as gigahertz. Yeah. The table in the back, inside cover of the book, is your metric prefixes. And you see I mentioned kilo, mega, giga, and the next one is tera. I don't think y'all are going to do any terahertz. You might, but that's awfully high frequency. I mean, incredibly high frequency. I think you'll probably be in the kilo, mega, possibly giga range, but that's probably about it. Okay. And just for example, they give some here. Radar and microwaves are measured in gigahertz. Frequency modulated FM radio is in megahertz. And AM radio, I'm pretty sure, so they've lost the thing here. Yeah, AM, amplitude modulated radio, is in kilohertz. Okay? So, like I said before, the symbol for period is, I thought they used capital T, and they do. So frequency is equal to 1 over period. I was calling it 1 over P is 1 over T. Okay? Frequency is F, capital T is period. Little t is time. Capital T is also a time, but that's the time period, the length of time it takes to go from one to another. Now, we have something else. Remember when I did up and down with the hose? Then you watch the thing move. If you were timing that, okay, you would see how much time it took for the wave to get from here to the end of the wall, or something like that. Well, then how far it traveled divided by the time would be its wave speed, or wave velocity. Okay? So that's the other issue that we have here. Propagation velocity. That's usually little v. Okay? Just like velocity usually is, little v. Now, velocity is usually in meters per second, some sort of length per time, right? Well, what in the world that we've been dealing with has a length involved with it? Lambda. That stands for length, right? So your velocity is your wavelength divided by your period. Wavelength divided by time. Length divided by time. Now, what is a 1 over t? Frequency. So you could also say lambda F. There's another way to express your velocity. Wavelength over period, or wavelength times frequency. Okay? Now, I think, now if Deidre was still here, she would insist on this, but we'll do it in honor of her, even though she had to leave. Oh, I know what I was going to do. We'll just do this. All right. I'll have to get my pen back every time. But, okay. All right. Here's example 1. Find the velocity Let me get my pen back. I said I was going to do it and then went right on as if I didn't have to. So we're looking for velocity of a wave with a wavelength. What symbol for wavelength? Lambda equal 2.5 meters. Pretty long wavelength. And a frequency. What symbol for frequency? Little f. Now earlier we may have mentioned little f as being a friction. We're not talking about friction now, so it's frequency in this chapter. Little f of 44 hertz. Remind me what a hertz is? Now this book uses strange notation. They call it per second. 1 second, exactly. So they do it this way and call it a per second, where that slanted line there is called the per, like miles per hour, miles per gallon. The per is that slanted line. So 44, when I say it, I usually say cycles per second, okay? That's what you're talking about. So what would be your velocity? What was the formula for velocity? Okay, lambda over period, if we knew the period, but since we don't know the period and we do know the frequency, what was the other one? Times frequency. Sure, or we could calculate the period from the frequency. We could have done that. So this will be 2.5 meters times 44 per seconds. And what does that give us? A little again? 110. And what would be the units? Meters per second. You got it. That's a good unit for a velocity. Meters per second. That's moving pretty quickly. 110 meters, that would be basically from one goal line to the opposite end zone in a second. That's moving, okay? That's moving pretty fast. And that's a low frequency, okay? Pretty slow. So 110 meters per second. Now, I think I'm going to get out of this slide and go back to the other one. And go from current slide and advance one. Yeah. Now we're going to do something they call superposition of waves. Okay? Now let's see what they're talking about here. Here we have a wave at the top. There's a wave. Wavelength, certain length, lambda indicated there. We aren't given anything about the time or the velocity or anything like that. All we know is a wavelength. Don't really know much about the amplitude either, except how it looks there. That would be how high it is above the equilibrium position. But here's another wave, in the B. This wave appears to be pretty close to twice the wavelength of the other wave. Okay? Because this is a little removed from that one, but this one's also a little removed from that one. So it looks like it's about twice as long a wavelength. Now, if those are equal times that are given there, that wavelength per time, this wavelength per time, they actually are going about the same speed, because it looks like if these are equal times, it looks like they could be. But we're not going to worry about that too much. What we're going to do is add these two waves. Okay? So drawn on the same graph, here's the A wave. Here's the B wave. Okay. Now, in every place, we're going to add the amplitude, you might say, but not the total amplitude, the magnitude, the height above. So both of these are positive, so this line's actually going up faster. But when this one starts going down, that one's still going up. So you reach the peak right about there where they touch, and then it starts coming down. Okay? Now, over here, this one's above the line, right here, this one's on the line. So this is right, all the amplitude is coming from the B wave. Okay? When you get down here, this one's going downhill, this one's actually negative here, so your wave is in between these two. Okay? Somewhere down here, this one's further down than this one's up, so you're actually below the line here. In fact, the place where this one is here, that one is there, they must be exactly the same because they added 0. After that, this one's pulling it down faster, that one's decreasing, this one's decreasing, so that's decreasing here. But then this one's going up, that one's coming down, but right there they meet. So therefore there must be 0 there. And then this one's going up, this one's going down. So that goes up for a little while, but then after a while this one drags it down, and that point, these points are the same, that's 0, and then it drags it down, and now they're adding negatively down here. And it goes through this cycle, and you notice you get a wave with two peaks, a big peak and a little peak, two valleys, a little valley and a big valley, and you can almost think of that as a pulse. Big pulse, little pulse. Your heart sometimes will go doot, 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 big, small, because your ventricle, am I saying it right? Are beating, and those are different ones, and that's why you have a little bit of a variation in pulse there. So we call this superposition of these two waves. Up here where they're adding, this is called constructive interference. Down here where they're subtracting from each other, this is destructive interference. Okay? Little bit of constructive, big destructive. Big constructive, and on like this. This is the result of the addition of those two waves. And that you can almost see there's a beat there. Da-dum, da-dum, da-dum. Two, a big one, small one. Okay? Now, they say here the addition is algebraic, you're just adding the magnitudes. And that's what we usually call how high above or below it is the magnitude. Okay. Now we're going to look at the concept of a standing wave. Let's see if we have a picture of that. Yeah, we're going to, I think. Okay. There's a special case with two waves combining, so there's no propagation of energy along the wave at all. Now that's sort of bizarre, okay? I may have asked this question before, and I'll probably ask it again. Have any of you been to the McWane Science Center? Okay. There is a wave, or there used to be a wave function generator over on one of the things, and you blow mist into the air and have strobe lights and stuff. And if you set the frequencies right, it looks like it's one wave that's just sitting there. It's really going bzzz, but the strobe light makes it look like just one wave. And it's actually moving like crazy, but not transferring any energy because everything's fixed in place. It's just sitting there. That's called a standing wave. Okay? We're going to get to it in a minute. We're going to build up to it with this. Okay? Now, here I go up and down with my hose. Okay? And it starts here. It started back here. It moved to here, moved to there. Ultimately, it's going to hit the wall. Okay? And then, amazingly enough, if the wall is fixed right there, not allowed to move up and down, then this wave actually reflects off the wall, but comes back in the opposite direction and goes that way. So not only, good deal, thank you. Okay, wait. Did you get the test last time? No. You didn't? Okay, let me go on and give it to you. I meant to stop when we had the test. Okay. Okay, hold on, don't go anywhere until I make a correction. Who else did not get one? Wait. This is the one we were doing, isn't it? Yeah, this is the matter. Who else did not get one? Didn't I have one correction to make on here? Or that was the last test, I guess. Anyone else? Anyone else? Okay, I guess this one didn't have any, or did it? What's that?
Chapter 12 too?
I think this is chapter 12.
It was 2 corrections you did on there for 50,000 pounds.
Okay, was that chapter 12 or was that the previous one?
That was the previous.
Yeah.
Well, wait. No, that's chapter 12. That's 50,000 right here on 3. That's it.
Okay, wait one. Okay.
It's 2 corrections. It was 50,000.
I may have given you the wrong test.
Those are 2 corrections he had. But that's chapter 12.
Okay. I'm getting myself
Like
confused.
this one you just gave out.
Okay.
On our last meeting, you gave us 2 corrections. That's supposed to be 50,000.
Okay.
That's supposed to be 60,000.
That is, I think. I didn't get. Oh, Deidre got it. Okay. Okay, that's the one you just turned in, wasn't it? Okay. Wait just a minute. Okay. The first test was on forces. Okay. Second test was on work and energy. The third test was on matter. Okay.
This is matter. Yeah. The one you just gave is matter.
There it is. Okay, yeah, I see it. I couldn't see it. Okay, you see question number 3? Okay. Have you ever seen anything that looks like this? 50,00. That makes no sense. There should be a third zero there. You see it? And then on the B part of the question, that should be 60,000, not 60,00. So those both have 2 zeros on them. 3 zeros after the comma. Okay? That's it. I knew it had to be that. Okay, did anyone else not get the test? Okay. And the lady who left early today, not Deidre, she got it right last time, but she left and I didn't know she was leaving and I didn't think about it. But when I finished the chapter, I meant to pass these out. But the rest of you got it. Good deal. Okay, the old gray cells ain't what they used to be. All right, so this is what's happening with a reflected wave. Now, I want you to imagine something. What if I stood there and went ding, 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 up and down, so there was a series of these going down here. Then after a while, they're bouncing off and going back, and if you timed it just right, this going up could be right at the time this is going down, and then they look like they just sit there with waves top and bottom and not moving anywhere, okay? That's what we mean by a standing wave, okay? So it's a little bit of a bizarre concept, but that's a standing wave. So let's see if we can, yeah, here's one. Now, here's what makes it a standing wave. If your disturbance is up there, and your distance from your disturbance to the fixed position is some half wavelength, you get a standing wave, okay? Because I don't know why they didn't draw the second one here. If you drew a dotted line here, that would be 1/2 of a wavelength, because it's going this way, the other half would be down here, that would be 1 wavelength. So if this was half, then it's going to be coming back the other half. So if that's 1/2 a wavelength, 2 halves, which is 1 wavelength, that's 1 complete wave, because now it's going the same direction, same speed, okay? This is 1.5 wavelengths, 2 wavelengths, and on and on and on. Those are standing waves, okay? If you're not exactly that, you get all kinds of chaotic things, like we saw before. Thump, 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 dop, okay? But with a standing wave, it just sits there, okay? Now, so in other words, if this length L between the disturbance and the fixed point, if that L is 1/2 of a wavelength, or any multiple of a half wavelength, then you can produce a standing wave. So those are the requirements there. All right. Now, this chapter actually has better slideshows than every other one we've done. Okay, this is interference and diffraction. Okay? Now, what we have here are 2 points of vibrations. Let's say we got a sound generator in a pool of water. You stick them down in there and you start generating sound. Okay? And the sound is producing waves. Okay? Now these seem to be on the same frequency and stuff because the waves seem to be going out at the same relative displacement and stuff. Okay, now which is the first thing they hit? I think they hit interference first. What you see happening here in a weird kind of way, you see sort of the rays that are coming out here? You see those? You're not just imagining them. That's where the waves are interfering with each other. Okay, right here. Okay. There's this, okay. One of them is on its way up, the other's on its way down. They interfere and they block each other out. Okay? Even though they were doing quite well up until that point. So those are your line of what they call the nodes, where they neutralize each other. And you see this figure shows this, because your waves are coming out of this one, the brown waves out of the upper one, the green waves out of the lower one, and where they happen to be coinciding, these are what we call the nodes. Okay? And that is your, basically maps your interference pattern. Okay? If the trough crosses a tress, the water level is nearly undisturbed. Okay? And those are your, they cancel each other out. Those are your nodes, and these are your lines of your nodes. Okay? Now, diffraction is the property of a wave that describes its ability to bend around obstacles in the paths. Okay? Let's see if we have a slide for that. Yeah, we do. You actually have a couple others in your book, that things you might see at the beach or somewhere. But this is something that represents, let's see, yeah. The one at the top we don't have, but here's the one. So here's what's happening. By the way, you call this a wave front. Okay? So here the wave fronts are coming down, but hitting this barrier here, barrier with a hole in it. So this part of the wave gets through, these parts get blocked, and these get partially blocked. So when they come out like this, bent and diffracted. Now, the energy coming down here, some of that gets blocked, and the energy coming out here, that's the amount of energy that was in here, that now is being dissipated because it's going over a wider area, so it's decreasing in time. This was pretty much coming boom, 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 you know, but this is now decreasing because the same energy is having to cover a larger area. So you do have some dissipation of energy there. Now that's a conceptual drawing. This is actually a wave pool you've done, and you could imagine this at a beach or somewhere, that your waves coming in, when they go through an opening like that, they dissipate this way. Okay? Now, yeah, this actually makes it look like they get bunched up in there and spread out here, but I can't account for that right now. Okay. Now, they do show a water park picture. Have any of you been to Splash Adventure? I never have. Huh? It has been a while. Do they have pretty decent? Yeah. I've never been there, but I know my mother-in-law lives up in Huntsville, and somewhere near there, I don't know if it's Madison or where, they have a really well-known old-time thing, and she used to take grandkids there all the time. Do you know what I'm talking about? It's what? Yeah, that's it. Okay. You've been to that one? It's pretty much fun, right? And what they do, they create their own in a fairly small space, and they show a picture here. Okay. All this is blah, blah, blah. Couple of examples, but all of that. Okay. So let's move on. Here's the simulated beach, the human-made wave pool. That's what it's called. And I imagine that's what they have at Point Mallard and I guess Placid Venture. I've never been there. Okay. The pumps create the waves and they get dissipated. Now, yeah, and there's a picture of the kids playing in it. Now, this wasn't created by man, but it wasn't completely natural either. We have friends who live in Munich, Germany, and we were up visiting them one time. In fact, we've been a couple times. And they have this place where the stream that used to run through the area, they built roads over it and stuff, and they funneled all the water into big culverts. And then finally they let it out. And where they let it out, there's so much water coming that right in this park in downtown Munich, people go out there and surf. Because it's coming out into a ditch, and for a little ways they can surf. And you wouldn't think in Munich, in the middle of town, way away from any open water, you could surf. And they were out there surfing like crazy. And this place sort of reminded me of that. But let's move on to 16.2. Now we're into the stuff we really need. Electromagnetic waves. Okay? Electromagnetic wave is a transverse wave. The energy is like this, but the wave motion's like that, perpendicular, resulting from periodic disturbance in an electromagnetic field. Not actually particle disturbance, field disturbance. Okay? And it actually, and just to make it more complicated, it's a three-dimensional thing. The electric field is going like this, the magnetic field is going like this, and the wave is going like that. It's a rather bizarre thing. We talked about wave velocity, right? Well, there is a wave velocity for electromagnetic waves. Does anyone want to make a guess about what that wave speed is? For electromagnetic waves, let me get my pen back if I can find it here. The speed of light. You're absolutely right. What we were calling V is now C. Electromagnetic wave radiation travels at the speed of light. Now, this is in a vacuum. In air, it'll slow down ever so slightly, but hardly enough to measure, okay? The speed of light. And that speed of light is, to 3 decimal places, 3.00 times 10 to the 8th meters per second. All right? Now, to give you a perspective of what that is, 10 to the 8th is a huge number, right? That's a 1. Well, let's take the 3. 3, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0. That's 300 million meters in a second. Now, to get a little bit of perspective on that, I've heard this before, I haven't actually measured it. That would be starting at, say, Quito, Ecuador on the equator and going around the world 4.7 times in a second. Okay? If you can imagine anything that fast, that's the speed of light. Around the entire Earth, more than 4 times in a second. That's fast. Now, before, what did we say our velocity equation was? We gave a couple of them. Lambda times frequency. Well, guess what? That's true here too. It's the wavelength times the frequency. Okay? Now, so just to give you an idea, the frequency is measured in cycles per second, so that's the upper scale here, going up as you go from left to right, whereas your wavelength is the lower scale, and that's going increasing from right to left, because these are, the product is a constant. Okay? So let's look at some of those. And by the way, C is always a constant. In the other one, V could change. Different energy, different whatever. C is a constant. A constant, not changing. Okay? So when frequency increases, wavelength has a decrease. When wavelength increases, frequency has a decrease. There's no getting around it because the C is a constant. Okay. Now, so let's do example 1 before we get to this. So let's go back to, I hate to do this because I'll lose my pen and everything, but it's not bad. Okay. Oh. My goodness. Yo. I know we're running short of time. Let's do example 1. The FM band, let me get my pen back. I said I had to do it and then I didn't do it. Okay. The FM band of a radio is centered around a frequency of 100 megahertz. Okay. And as I just told you, that was the frequency. Okay. Find the length of an FM antenna if each arm must be a quarter of a wavelength. Okay? So we want the length of a FM antenna if each arm has to be a quarter of a wavelength. Well, we don't know anything until we know the wavelength. Okay? How can we get the wavelength if all they gave us was frequency? And guess what? If we're talking about radio waves, those are electromagnetic waves. So what formula do we know? C is equal to lambda F, right? And this is 3.00 times 10 to the 8th meters per second, right? Is equal to lambda, which we don't know, that's what we're looking for, times 100 million, mega means million, 100 million per seconds. Okay, strange way to do it, but that's how they refer to hertz, as per seconds. Okay, so what you reckon we're going to do? Second? No, okay, not multiply. We want to get the lambda, so we're going to divide. So we'll do divide by 100 million per seconds. Okay? Well, this per second is going to cancel out that per second. And, oh, you know, it would have been better if I had done this as 1.00 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 per seconds. And now the 10 to the 8ths cancel out, and 1 will go into 3. And we divided this by 1.00 times 10 to the 8th also per second. So these canceled out. And that gave us a lambda equal to, and all we got left are meters. 3.00 meters. Because everything else canceled out. So that's a 3-meter wavelength. That's your lambda. The second part of the problem said, not the second part, the second phrase in there, if each arm must be a quarter of a wavelength. So what's a quarter of 3 meters? Divide that by 4, 0.75 meters. That would be what each arm would be. Oops. An extra 0 at the end because we had 3 significant digits there, 3 significant digits there. We need 3 significant digits there. So each arm must be 3/4 of a meter. Okay? Now, what is 3/4 of a meter? If this is a meter, 3/4 would be maybe about midway to my forearm here, from here to there. Okay? Or maybe the length of my arm. That would be pretty close to 3/4, somewhere about. Okay. Now, they're going to talk about the electromagnetic spectrum. So let's get back to the other slide. Okay. And that's where we left off here. So go from current slide. And I don't know if I need my pen or not, but this time I'm going to remember to activate it. So here we go. All right. So this is the electromagnetic spectrum. The reason we can set it up this way is because the speed of light is constant. Okay? Now, I'll just give you a little hint here. The lower the frequency, the lower the energy. The higher the frequency, the higher the energy. Because when frequency goes up, wavelength goes down. The longer the wavelength, the lower the energy. Now, this is just in general, so other things could go into it. But I said that for this reason. What we're talking about here is 10 to the 4th. These are cycles per second. Okay, I was going to say, where's my frequency? Cycles per second. So we're not even down in the kilohertz range here. This is starting in the tens of kilohertz. This is megahertz here. So this is called your broadcast band, and that's where most radio stations are, especially AM, maybe a little bit lower. Okay? Your ham radio operators, anyone know a ham radio operator? Okay, I had a roommate in college who was one. These are what they call short waves. I think these are also, now, it's been a long time since these were popular, but Citizens Band, CBs, do you remember? Y'all were too young to remember that, okay. That was a big deal back in the 60s, I think it was, because truck drivers had them and they had music about them. It was a big deal. Everybody was buying CBs. They lasted maybe a few years and no one used them anymore. Your TV bands are up here, and that sort of overlaps with some of your FM. So that's up in the megahertz range, okay. Then you have the microwaves, okay. Now, why are they called microwaves? Because your wavelengths are getting pretty small there. Now, what do we do with microwaves? We cook with them, okay? Exactly. Does anyone know how that works? You notice the oven, the microwave oven, doesn't get hot. How does it cook your food? Well, they set up the wavelengths in that so they represent the wavelength, the naturally occurring wavelength and frequencies of the water molecule. So they set this up so these are flying through there. These excite Have you ever heard of resonance? We're going to talk about that a little bit later. Have you ever tried to push a car off? Or seen someone try? Who can push a car? Well, actually, you can't. Just get out of gear and brake off, and then what you do is get it rocking, right? And when it's rolling forward, then give another push. Give another push. It's a lot like pushing a kid in a swing. You don't start with as high as you can go and go. You start low, and then you push it just the right time, and soon you can get them really flying. Push harder, higher, or stop, or whatever, okay? That's what resonance is. If you do that with microwaves, water, the food cooks basically from the inside out. The water molecules get so excited, they heat the food from the inside. Now, they also set them up so they react with oils, which are pretty close to water in the natural frequency too. So the oils also get active like that. And you cook your food without adding that much heat. But that's just one thing we do with microwaves. What's another thing? What you got there in your hand? And how does that send signals? You see these towers? What do they call those towers? Microwave towers. Okay, they're sending them by microwaves. Okay? So you got your TV bands, your radio bands, those are down here. Microwaves actually fall in radio waves. Now when you get up here, you have what we call infrared waves. And that's basically heat. Okay? Did any of you drive over here tonight? Where were you driving from? Home or work or somewhere like that? Home? Okay, did you have your car in sort of a protected area? No. I didn't either. Mine was out in the parking lot on the Bessemer campus. And because we had rain every day, it seemed like, I didn't want to leave my windows down this morning. So I had them up. When I opened that car door, my word, it was hot in there. And here's why. The electromagnetic radiation from the sun, visible light from the sun, was shining on the windshield and the windows all around the car. And when it did go through the windows, it lengthened its wavelength just a little bit, which dropped it out of the visible light down here to infrared, which was heat. But that heat, a little bit lower energy, not as energetic, could not go out of the glass. The light could come in because that was higher energy. It couldn't go out, and then the car got really, really hot. And that's what happens with kids and pets. They've started putting those signs on the interstate. Look before you lock, because don't leave a pet, don't leave a kid in the car in this kind of heat, because they've had deaths because of it, okay? And it's really bad. What do we call that effect? Light lengthening when the infrared radiation lengthening when it comes through, visible light radiation lengthening when it goes through something and becoming heat. That has a name for it. People who grow plants use them. Greenhouse effect. Have you ever heard of that? You know what a greenhouse is? Yeah. Even in the middle of winter, sometimes those things are toasty inside because, just like your car, the light comes in, lengthens, becomes heat, it can't escape. Now, sometimes it gets so cold at night you have to heat them up some at night, but in the daytime, they stay toasty. If it's sunshine. Now, if it's a foggy day out, cloudy day, and it's really cold, you might need to add heat then too. That's the greenhouse effect. Now, what else do we talk about greenhouse effect these days? Global warming. Because our atmosphere acts the same way. We are far enough from the sun that we shouldn't have life on us. We're too cold, except we have this nice big blanket called our atmosphere around us that gets the heat light in, changes the heat, and then it doesn't escape. Not much of it anyway. That's why we can exist as a planet as far from the sun as we are. Okay? The greenhouse effect. But, have you heard them talk about greenhouse gases? carbon dioxide levels are now probably higher than they have ever been in history. And there's plenty of methane in our atmosphere and stuff like this. These are greenhouse gases. They'll call them that because they act like thick glass that lets more heat, that traps more heat and doesn't let it escape. That's why they think, all indications are we have global warming. Because technically, by all views of everything, the Earth should be in a cooling cycle right now, and yet it's in a warming. If it was supposed to be in a warming cycle, we'd be in serious trouble because we're trapping even more. So this could be pretty bad. All the light that gets through our atmosphere pretty much is in this range right here, the visible light spectrum. Now, I don't know if you know the little acrostic, red, orange, yellow, green, blue, indigo, violet, Roy G. Biv. That's what comes through. To the left of that is infrared, that's the heat that gets trapped. To the right of that is ultraviolet, which isn't too good of stuff. I mean, yeah, black lights, that kind of stuff, but it's not really healthy stuff. I have precancerous place on my nose right here. I have to put sunblock on it every day. Why? Because ultraviolet light has damaged the cells. When I was a kid, I grew up on the farm. I was outside all the time driving tractors. I could never wear a hat. They always blew off, and I was out in the sun too much. I've had one basal cell removed here. I'll probably be being carved up the rest of my life, as that happens. Of course, some of y'all have a lot more melatonin in your skin than I do, and so I'm a lot more susceptible to that. No, keratin, isn't it? Melatonin, okay, melatonin, okay. So ultraviolet causes wrinkles. It's what causes sunburn. It's what causes skin cancer. And it's what causes cataract. I've had the cataract moved from my right eye. This one's growing, but not quite bad enough to be removed there yet. Not good stuff. X-rays, even higher energy, higher damage. Gamma rays, you don't want to go there, okay? Fortunately, our atmosphere blocks out most of this, but some gets through that blocks out almost all of this. Thank you, atmosphere. But the atmosphere also traps the heat. Thank you, atmosphere, except we got too much carbon dioxide in it. I guess by everybody moving around, we must be out of time, okay? But we pretty much finished the section right there. So homework exercises here. If you choose to do them, any of the odds 1 through 17. And guess what we start with next time? Sound waves. That's what y'all are going to be dealing with in sonography, right? So this is where we've been heading. That's where we'll be next time. Good deal. Thanks for staying with us for the extra 30 minutes, the last 3 times. And we won't meet on Thursday. Sorry about that. And you have heard the good news, bad news situation next week, right? The bad news is the 4th of July falls on a Wednesday, so there's no school on Wednesday. But the good news is we meet Tuesday, Thursday. It won't bother us any, will it? All right. Good deal. With that, y'all can go. All right. Have a good long weekend, and we'll see you next week.